All right, let's go. Number 10. The Monty Hall Problem. You're on a game show. 3 doors. Behind one, a car. Behind the other 2, goats. You pick a door, say, door 1. The host, who knows exactly what's behind every door, opens door 3 and shows you a goat. Then he asks, do you want to switch to door 2 or stay? Most people stay. It feels like a 50-50 coin flip now. 2 doors left, why move? Here's the part that breaks brains. If you switch, you win 2 out of 3 times. Not half. 2/3. Staying wins only 1/3. The reason is buried in what the host's reveal actually tells you. He didn't open a random door. He opened a door he knew had a goat behind it. That single constraint smuggles information into the game, and it tilts the odds toward the door you didn't pick. Your original choice was made blind, with 1 in 3 odds. The other 2 doors, combined, always carried 2 in 3 odds, and once the host eliminates one of them for you, all of that probability collapses onto the single door he left standing. In 1990, a columnist named Marilyn Vos Savant published the correct answer, switch, in her magazine column. What followed wasn't quiet disagreement. Thousands of letters arrived, many from people with PhDs. Some from mathematicians who taught probability for a living, telling her, in print, that she was wrong, that she should be embarrassed, that she'd insulted the intelligence of her readers. She hadn't. She was right, and nearly all of them were wrong, and it took years for the field to fully admit it. Sit with that for a second. This isn't a paradox from the frontier of theoretical physics. It's a problem simple enough to run on a game show, and it fooled people whose entire careers were built on getting probability right. If your gut can fail this badly on 3 doors and a goat, what else is it getting wrong every single day, in situations with far more than 3 doors? Your intuition just lost, on national television to a math professor's worst nightmare. That's the promise of this whole video. 10 times over. Number 9. The birthday paradox. Picture a room. Not a big one, 35, 40 people, tops, a wedding, a classroom, a work meeting. Here's the claim. In a room of just 23 people, there is better than a 50% chance that 2 of them share a birthday. Not a specific date. Any match between any 2 people. That sounds broken. There are 365 days in a year. 23 people is nothing next to that. It should take hundreds of people before a coincidence like that becomes likely. It doesn't. At 23 people, the odds already tip past 50%. At 70 people, the probability exceeds 99.9%. A shared birthday becomes almost a certainty. The trick is what you're actually counting. You're not asking, does anyone share my birthday? That comparison really would need hundreds of people. You're asking whether any pair, out of every possible pair in the room, matches, and the number of possible pairs grows far faster than the number of people. 23 people generate 253 distinct pairs. 253 separate chances for a coincidence, all stacked against a denominator of only 365. The odds aren't comparing one person to the room. They're comparing every person to every other person. Simultaneously, think back to the last classroom you sat in, the last wedding, the last big meeting, the last flight you boarded. If it had 23 people or more, the odds say a birthday match was sitting inside that room, quietly, and nobody in it ever noticed. It's not a coincidence waiting to happen. It's one that almost certainly already did. The room you're picturing right now had a hidden coincidence in it. You just never checked. Number 8. Simpson's Paradox. In 1973, the University of California, Berkeley, faced a very public, very serious accusation. Its graduate admissions appeared to discriminate against women. The overall numbers backed it up. Men were admitted at a noticeably higher rate than women across the entire graduate school. It looked like exactly the kind of case that ends in a lawsuit and a headline. Then someone broke the numbers down by department instead of looking at the school as a whole. And the pattern didn't just weaken, it reversed. When researchers examined admissions department by department, most departments individually favored women by a small but real margin. The bias in the aggregate simply wasn't there in the parts that made it up. What happened is that women disproportionately applied to the most competitive departments, the ones with brutally low acceptance rates for everyone, men included. Men applied more heavily to departments that admitted almost anyone. Add every department together into one big number, and that difference in where people applied gets mistaken for a difference in how they were treated. Each department, on its own, was defensible. Stack them, and the total lied. This is Simpson's paradox. A trend visible in every individual group can completely invert once those groups are merged into one. It's not a rare statistical glitch. It's a structural trap sitting inside how averages work. And it's been rediscovered, quietly, in medical trials and hiring data and sports statistics ever since Berkeley. Every headline number you've ever read, every this treatment works better, every this group outperforms that group, could be hiding this exact reversal one layer beneath the surface. And a single top-line figure gives you no way to check. You cannot trust a statistic just because it's a statistic. Number 7. Zeno's Paradox. Achilles and the Tortoise. Around 450 BC, a philosopher named Zeno of Elea proposed a race. Achilles, the fastest man in the story, gives a tortoise a head start. The race begins. By the time Achilles reaches the point where the tortoise started, the tortoise has crawled a little further ahead. By the time Achilles closes that new gap, the tortoise has moved again. And again. And again, forever, Zeno's conclusion. Achilles can never catch the tortoise. Not it takes a long time. Never an infinite number of gaps stand between them, and you cannot cross an infinite number of anything. Obviously, Achilles catches the tortoise. Faster things overtake slower things with a head start. Everyone watching the race knows this. But Zeno wasn't wrong about the logic. For over 2,000 years, nobody could explain exactly where the argument broke. Not until the formal development of calculus and the mathematics of convergent infinite series showed something strange. An infinite number of shrinking distances can still add up to a finite total distance, covered in a finite amount of time. The math resolves the arithmetic cleanly. Whether it resolves the underlying logical puzzle of actually completing infinitely many discrete steps, philosophers still argue about that today. Here's the part that should bother you personally. You crossed a room today. To do that, by Zeno's logic, you had to cover half the distance, then half of what remained, then half of that, on, into an infinite sequence of ever smaller steps. Mathematics can tell you the numbers add up. Nobody has ever fully explained how you manage to actually finish an infinite sequence of anything in a finite afternoon. You've solved Zeno's paradox physically every day of your life without ever understanding how. Number 6. Hilbert's Grand Hotel. In 1924, the mathematician David Hilbert proposed a hotel to illustrate a problem with infinity, a hotel with infinitely many rooms, every single one occupied. Completely full, no vacancy. A new guest arrives, the hotel accommodates them anyway. The trick, ask the guest in room 1 to move to room 2. Room 2 moves to room 3. Every guest shifts up by exactly one room forever down the infinite hallway, and room 1 opens up. A full hotel just created a vacancy out of nothing. It gets stranger. An infinite bus arrives, carrying infinitely many new guests. The hotel still fits them all. This time, every current guest moves from their room number to double their room number. Room 1 to room 2, room 2 to room 4. Room 3 to room 6. Every even-numbered room is now occupied by an existing guest, and every odd-numbered room, infinitely many of them, stands empty, ready for the infinite bus. A hotel that is completely full and can never actually be full, both true at the same time about the same building. This isn't wordplay. It's a direct mathematical consequence of how infinite sets behave. And it reveals something you can't intuit from ordinary experience. Infinity doesn't act like a very large number. A very large number runs out. Infinity, treated properly, simply doesn't, and the moment you try to reason about it using rules built for finite things, you get contradictions like a hotel that has no room and endless room. Simultaneously, nothing in your ordinary life prepared you to reason about a quantity that behaves like this. Number 5. Cantor's diagonal argument. In 1891, a mathematician named Georg Cantor proved something almost nobody wanted to hear. Not all infinities are the same size. Specifically, there are more real numbers between 0 and 1 than there are whole numbers, total, even though both sets go on forever. The proof works like this. Assume, for the sake of argument, that someone has managed to list every real number between 0 and 1. In some order, an infinite list. Cantor then builds a brand new number, one digit at a time, by going down that list diagonally, taking the first digit of the first number and changing it, the second digit of the second number and changing it, and so on. The number he builds this way is guaranteed to differ from every single number on the list by at least one digit, which means it was never on the list, which means the list, however it was constructed, however carefully, could never have been complete. The infinity of whole numbers and the infinity of real numbers are, provably, permanently different sizes. Hilbert's hotel worked because all the infinities involved were the same size, endlessly shiftable. Cantor just proved that assumption doesn't always hold. Some infinities are bigger than other infinities. The mathematical establishment did not take this well. Fellow mathematician Leopold Kronecker called Cantor a scientific charlatan, publicly, and worked to block his academic career for years. Cantor later suffered a breakdown and spent time in a sanatorium, not proof his math was wrong, but a sober measure of exactly how radical and how personally costly this discovery was in its own time. There isn't just one infinity. There may be infinitely many different sizes of infinity stacked on top of each other, and the man who proved it was told to his face by the leading mathematicians of his era that he'd lost his mind. Number 4. Gabriel's horn. Here's an object you could fill completely, with a finite amount of paint but never coat on the inside. Not with an infinite amount of time. Never take the simple curve described by y equals 1 over x for every x greater than or equal to 1 and spin it in 3 dimensions around the x-axis. You get a horn, like a trumpet bell, stretching out toward infinity, getting thinner and thinner the further out it goes, but never quite reaching zero width. Do the calculus on that shape, and 2 facts sit side by side, both proven, both true. The volume inside the horn is finite. You could calculate exactly how much liquid it takes to fill it, and pour that amount in, and it would fill up completely. But the surface area of the horn, the inner wall you'd need to coat with paint, is infinite. It never stops growing. You could pour paint into the horn forever, and forever wouldn't be enough to cover the surface that same paint is technically already touching. The resolution isn't a trick of language. It's that the horn narrows fast enough that the volume calculation converges to a fixed number, while the surface area calculation, measured along that same shrinking tube, diverges and never settles. The horn runs out of stuff long before it runs out of surface, finite and infinite, coexisting in the exact same object, touching the exact same paint at the exact same moment. Number 3. The Banach, Tarski Paradox. In 1924, mathematicians Stefan Banach and Alfred Tarski proved something that sounds less like mathematics and more like a magic trick that accidentally turned out to be real. Take a single solid sphere, cut it into pieces as few as 5, and reassemble those pieces, using nothing but rotation and repositioning, into 2 solid spheres, each one identical in size to the sphere you started with. No stretching, no adding material, no cheating with scale. One ball becomes 2 balls, both full size, using only the material that was already there. The trick is in what the pieces actually are. They are not shapes in any ordinary sense, not chunks you could cut with a knife, or even draw. They're infinitely detailed, non-measurable collections of points, so intricately scattered that they cannot be constructed, visualized, or built in the physical world. They exist purely as a logical consequence of accepting something called the axiom of choice, a foundational rule of set theory that on its own sounds almost too reasonable to argue with. It simply says that given any collection of non-empty sets, you can choose one item from each. That's the whole rule. And accepting that one reasonable-sounding rule is enough to force this impossible doubling of a sphere into mathematical existence. Decades later, some mathematicians still treat the axiom of choice with open suspicion. Not because anyone has found an error in Banach and Tarski's proof, but because the world that proof describes doesn't feel like it should be allowed to exist. A single, quiet assumption about choosing from sets, and somewhere downstream of it, a ball splits into two balls. You accepted the axiom before you ever heard its name. You just never knew what it was quietly permitting. Number 2. Russell's Paradox, the crisis that nearly broke mathematics. In 1901, the philosopher and mathematician Bertrand Russell asked a question that sounds almost too simple to matter. Consider the set of all sets that do not contain themselves. Does that set contain itself? Follow it through. If it does contain itself, then by its own definition, it shouldn't. If it doesn't contain itself, then by that same definition, it should. Either answer collapses immediately into its own contradiction. There is no consistent way to answer the question at all. This isn't a party trick. At the turn of the 20th century, set theory was being positioned as the bedrock underneath all of mathematics, the foundation everything else would be built on top of. Russell's question exposed a contradiction sitting directly inside that foundation. The philosopher and logician Gottlob Frege had spent his career constructing a formal logical basis for arithmetic itself. The second volume of that life's work was already at the printer when Russell's letter reached him. Frege wrote back and appended a note to his own book, admitting, in print, that the foundation he'd just finished building had collapsed underneath him. The plain language version is a barber in a town who shaves every man who does not shave himself. Does the barber shave himself? Both answers contradict. A small, almost funny puzzle that turns out to be the exact same logical trap Russell found buried inside the mathematics everyone was relying on. It forced the entire field to spend the next 3 decades rebuilding its own foundations from scratch, culminating in a new, more careful framework, Zermelo-Fraenkel set theory, assembled piece by piece between 1908 and 1922. Mathematics is not a fixed pre-existing truth that people simply uncover. It's a structure people build, by hand, out of assumptions and wants. An entire field had to tear that structure down and build it again, because one question broke it. Number 1. Gödel's incompleteness theorems. In 1931, less than a decade after mathematicians finished rebuilding the foundations of their field in response to Russell's paradox, a logician named Kurt Gödel proved something far worse than a single contradiction. He proved that any mathematical system powerful enough to describe basic arithmetic will always contain true statements that cannot be proven true from within that system. Not statements nobody has proven yet. Statements that structurally cannot ever be proven, no matter how long anyone works on them, using only the rules of that system itself. Worse still, Gödel proved the system can never verify its own consistency from the inside. A mathematical framework can never fully prove, using only its own rules, that it isn't secretly hiding a contradiction somewhere within it. Every other item on this list attacked one specific problem. A game show. A hotel. A sphere cut into pieces. Gödel's theorems don't attack a problem. They attack the entire possibility of a complete, self-verifying mathematics, any mathematics, built on any foundation, no matter how carefully constructed. Even a perfectly repaired foundation, rebuilt from the wreckage of Russell's paradox, could never be complete. There will always be true things it cannot reach, and it can never even tell you, from the inside, whether it's broken. Every number, every proof, every equation you have ever trusted rests on a system that cannot fully vouch for itself. 10 items. A game show, a hotel, a sphere, a question about a barber. None of them are edge cases sitting at the outer limits of obscure mathematics. Every single one sits at the center of the tools we use to reason about reality itself. Probability, infinity, geometry, logic. The universe isn't confused about any of this. It never was. We are the ones building the frameworks, and one by one, those frameworks keep showing us exactly where they end. If you want to see more videos like this, click the video on screen now.